last time we were talking about linear free energy relationships. We talked about this parameter sigma, which we derived from benzoic acid deprotonation, and whether or not when you put a substituent at the para position, the deprotonation reaction is more or less favorable. And we saw that you can use these numbers, these sigma values, as a way to rank functional groups in terms of how electron donating versus withdrawing they are. For the benzoic acid reaction, the K value gets larger, meaning deprotonation gets more favorable when you have an electron withdrawing group. So the withdrawing groups have positive values for sigma, the donating groups have negative values for sigma. And then we talked about how you can compare other reactions to the benzoic acid reaction to get a sense for whether this new reaction you're studying is similar or different than the benzoic acid reaction. And remember, we're looking at two different things. We're looking at the magnitude of the slope and the sign of the slope, right? So for benzoic acid deprotonation, if you plot sigma values versus the ratio of a rate or a equilibrium constant with a substituent versus without, you're going to get a line with a positive slope. And for the benzoic acid reaction, that slope is 1. For everything else, we're going to compare those values. So here's a comparison we ended on. This is the Sn1 solvolysis reaction. Solvolysis is a term that's used to describe reactions where a leaving group leaves and a solvent molecule replaces it. Solvolysis because the solvent is lysing or breaking a bond. In any case, if you run through a bunch of substituents here and then see what the impact is, we made a few predictions, right? The Sn1 transition state would be for chloride leaving and would involve a substantial buildup of positive charge on the carbon adjacent to the benzene ring. How do we know that that's the case? Well, we predict that it's the case because we're going from a low energy starting material to a high energy carbocationic transition state, or intermediate rather, and by the Hammond postulate, the transition state should resemble the carbocation. So we predict a buildup of positive charge here in the transition state for the Sn1 reaction. However, we expect not withdrawing groups. Withdrawing groups made the benzoic acid deprotonation more favorable, but here, because we're building up a carbocation or positive charge on this carbon, we expect donating groups to be more favorable, right? So if we were to plot for this reaction log of whatever rate constant versus the one with hydrogen, and then have sigma values where negative is donating groups and plus is withdrawing groups, we would expect to see the highest rate for the donating groups and the lowest rate for the withdrawing groups. So we would see the slope, the rho value, less than 0. In terms of its absolute magnitude, we would probably expect a substantial dependence. I don't know whether or not you could say whether rho should be -1 or less than -1. In some ways, because in the benzoic acid reaction, you'll notice that the negative charge on the carboxylate is not conjugated to whatever group we put here. So even though the nitro group does make the deprotonation more favorable, it's not because the negative charge here can come down out here. At best, what happens with the nitro group is that you can have a resonance structure where you put a positive charge adjacent to the carboxylate group. So for the benzoic acid reaction, you have this weird combination of both resonance and inductive effects. Resonance puts the positive charge in the ring. The inductive effect allows that electron deficient ring to suck electron density out of the carboxylic or the carboxylate. So it's possible, in contrast here, if we were to put like a methoxy group here, we can draw a resonance structure for a carbocationic intermediate in which, the donating group at sort of the X position can actually donate completely into that positive charge. That is, the positive charge in the intermediate and in the transition state could be directly stabilized by resonance. And so we might expect to see a rho value that's even higher in magnitude than for the benzoic acid reaction. In contrast, if the mechanism were SN2, in the SN2 transition state, there's not a substantial buildup of positive charge at the carbon, especially if the nucleophile and the leaving group are leaving at similar rates. And so we would see still probably a negative slope for rho. Probably there's some small delta positive here to that could be stabilized by electron donating groups, but we expect the magnitude to be much, much lower than for the SN1 mechanism. So we could do those experiments and see what the results were, and that would give us evidence for one mechanism versus the other. Or we could make life simple and make a chiral starting material and then show that stereochemistry was lost. However, that's kind of a bummer to do. It's expensive to get a chiral compound and then to watch your stereochemistry just go away is painful. Okay. I will tell you it's difficult to keep straight and memorize whether rho should be positive or negative and whether a sigma value should be negative or positive. So I'm not going to ask you to memorize sigma values. Just rely on your intuition. Electron donating groups should destabilize negative charges and stabilize positive charges, and you'll be okay. And if you need sigma values, I'd provide them in a table. Okay, and if I were to ask a question that required you to make a prediction, I would phrase it in a way that would not require you to have memorized sigma values. So let me show you an example of a reaction of a study where Hammett parameters helped to distinguish between two possible mechanisms. And the story is a little bit convoluted, but it starts with a molecule called an aryl carbamate. A carbamate is, and if you don't already know this, you'll learn it. A carbamate is a carbonyl sort of at the CO2 oxidation state. It's got one sigma bond to an oxygen and then another sigma bond to a nitrogen. We call this an aryl carbamate because you've got the arene ring here. And then we'll have some R group on the nitrogen and then a hydrogen there. So this is a aryl carbamate with an amide or a amide type proton. And in the reaction for hydrolysis of the aryl carbamate, and I think this is under sort of basic conditions, is it catalyzed or I can't remember. In any case, the hydrolysis reaction involves first release of the phenol leaving group, and at the same time you temporarily form what's called an isocyanate, I think, and then the reaction proceeds on in other steps that aren't that important to us, okay? And the mechanism for this reaction, at least when you have a hydrogen there, is not what you would think. It's not actually for the hydroxy group to attack the carbonyl carbon, but instead there's evidence that first, in a fast step, you remove a proton. Let's see. So actually, I'm going to mechanism A. And mechanism A is for carbamates that have that proton. In a fast, probably pre-equilibrium step, you remove this proton from the carbamate nitrogen. And the conjugate base now has a negative charge on that nitrogen. And that lone pairs from that nitrogen can kick up to the carbonyl carbon and kick off the phenol leaving group to give you should have started smaller, sorry, to give you the products that I drew above. And again, this isn't the end of the reaction, but what happens next isn't necessarily important to what we want to do. Okay, so that's mechanism A. Now, there's an alternative that only seems to matter when the carbamate nitrogen has two R groups on it, such that there isn't a proton there to be removed. Okay, so naturally, if you altered your structure such that you had an R group here and an R group there, well, friends, then there's no hydrogen on that nitrogen to remove, and so we attack the carbonyl carbon. We get the familiar tetrahedral intermediate that we maybe originally expected. Then, right, electrons kick down and the phenol leaves. And, oops. And what we have here is what's called a carbamic acid. Actually, this is what you would get if you added water to the carbonyl of the isocyanate. So don't worry that these look different. We've gotten to the end of the reaction there. So, all right. So if you do Hammett analysis for these two different kinds of reactions, if you vary X and then plot the rate of the reaction for the X group over the H group versus sigma values, sigma parameters, Hammett parameters for the benzoic acid reaction, you observe a slope of 3 for this is the rate determining step. All right? Now, the fact that, what do we interpret from here? And let's see if it makes structural sense. The fact that the slope is positive means what? What does that tell us about the nature of charge in the transition state?
Charge in transition state is negative.
Right. Charge in transition state, buildup of charge in the transition state has to be negative because buildup of negative charge in the transition state, sorry. And the reason we know that is because the reaction is slower for groups that have negative sigma values that are electron donating groups, and faster for groups that have positive sigma values or are electron withdrawing groups. Does that make sense? Well, sure, because in the transition state, there's going to be a lot of buildup of partial negative charge on this oxygen that is conjugated to the X group. You see that? Does that make sense? What we're saying, if the fact that rho is positive here means that this reaction is similar to the benzoic acid reaction in that in the transition state of the rate determining step, there's a buildup of negative charge somewhere close to where this X group is.
So, just, I guess, to like make this similar to the reaction we did before, was that like the SN2?
So this is the reaction we did before is opposite because it's a buildup of positive charge in the transition state. So if rho is negative, if the slope is negative, then you infer you got a buildup of positive charge in the transition state.
Yeah, so like, but I'm saying like the bottom where you have like the negative nucleophile, and we established that it's not SN2, it's SN1, right?
So if I didn't show you any data for this reaction, but if we observed, for example, that rho was positive, if we observe for this reaction that rho is negative and large in magnitude, then those data would be consistent with SN1. Yeah. So it's just all about, is the rho value, the slope you get when you compare rate of having X here versus hydrogen there, is that with the sigma values from the benzoic acid reaction, what does that rho value tell you about the transition state of the rate determining step? If rho is positive, that means the transition state has similar features to the benzoic acid deprotonation transition state. That is, there's partial negative charge in the transition state. If rho is negative, that means there's positive charge in the transition state. It's inconvenient because it's backwards. I didn't make this stuff up, and so you kind of have to try your best to follow along. All right, so the fact that rho has a positive value means that the transition state is similar to for this reaction is similar to that for benzoic acid deprotonation, in that if this is the rate determining step, you expect the transition state to have a buildup of partial negative charge at that oxygen. Okay? The fact that it's 3, the large magnitude of rho, tells you it's more sensitive than the benzoic acid deprotonation. Any sense for why that would be the case? And let me just show you the corresponding structure from the benzoic acid deprotonation. Why might you expect mechanism A to be more sensitive than the benzoic acid reaction where rho equals 1?
In A, the benzoic acid has a possibility of decomposition, but then in this structure of interest, the negative charge is
Right, the negative charge is on this oxygen. Okay, good. So actually with benzoic acid, you have delocalization of negative charge. I hadn't necessarily thought about that. What about the influence of this R group or this X group on the negative charge? Is it possible to conjugate and to move this negative charge such that it wouldn't be on the carboxylate anymore? Not really. You can draw a resonance structure where, as we said a little bit earlier, you can draw a resonance structure like this, but that's as good as you can do. And in contrast, if you have negative charge on the phenol and a nitro group, you can definitely do delocalization because that oxygen that has the charge in the conjugate base is directly conjugated with the nitro group. So that's one reason why you'd expect this reaction to be more sensitive than the benzoic acid reaction. Okay? Now let's consider mechanism B, and the rate determining step here is the formation of the tetrahedral intermediate. So that's this step. The rho value for this reaction is 1, So it's a lot lower than the rho value for mechanism A. Can you think of a reason why you'd expect that rho value here, which is 1, to not be as great as it was for mechanism A? Remember, the fact that it's positive, rho is positive, tells us this reaction is similar to benzoic acid deprotonation in that you expect a buildup of negative charge somewhere in the transition state. But the magnitude tells you not as much charge, or perhaps not as close charge building up in the transition state as in mechanism A. So any reason why you'd expect this group to not influence this rate quite as much? Go ahead, Heather.
On the first part of it, that like negative's a lot further away.
Right. The negative that's going to build up is on the carbonyl oxygen, which is not directly conjugated to the X group. So we're back in a situation similar to the benzoic acid case, where yes, electron withdrawing groups would put positive charge here, and that could, through an inductive effect, stabilize the buildup of negative charge here, but certainly not as effective as direct conjugation. Okay, so we can use Hammett parameter analysis and these rho values to discern whether a reaction is proceeding through mechanism A or mechanism B. Now enter, all of that's actually probably not the new thing about the paper that was written here. This paper isn't that new, actually. It's from the 90s, so but the textbook was written in the early 2000s, so at the time it was written, it was sort of recent. The researchers had an idea, and that is, could they create a catalyst that would allow an aryl carbamate of this kind. Sorry, let me back up. The researchers wondered, it was known that if you have a proton on the carbamate nitrogen, you go through mechanism A. The researchers wanted to know, can I develop a catalyst that forces an aryl carbamate with a hydrogen here to instead go through mechanism B? Can I disfavor the deprotonation and favor attack of the carbonyl carbon? So what they did was they built a molecule that they thought would resemble the transition state for mechanism B. These are called transition state analogs. And it's thought that, why would you want to do this? Well, it's thought that enzymes work not by stabilizing starting material or products, but actually by binding the transition state, lowering the transition state energy. We'll talk about that, I think, at the end of today's class. So what the authors wanted to do was they said, let's build a transition state analog. Let's build something that looks like that tetrahedral intermediate. We'll put an R group here. And phosphorus here, negatively charged oxygen there, NH, and then some R group. And then they used a chemical biology technique. They developed an antibody to this transition state analog. How do you do that? Well, I think you actually have to take an organism and inject it with the compound and try to grow up antibodies. Probably you end up making a monoclonal antibody via the hybridoma technique. You want to know more about that, Dr. Savage can sure tell you. I probably can't. But what they did is they developed an antibody which bound this transition state. So now they have, and they asked, will that antibody catalyze via mechanism B? Because it binds the mechanism B transition state. So their big test of their hypothesis was to now take an aryl carbamate. Oh, it's an aryl carbamate ester, sorry, whatever. With a proton on the carbamate nitrogen, and then some R group here. And then they did the hydrolysis reaction in the presence of the antibody. And of course, that would release the phenol and the carbamic acid and water. And then they did a Hammett analysis to see what the rho was. Okay? And the rho for this reaction, as catalyzed by the antibody, was 0.526. Now, compare the rho values for mechanism A versus mechanism B. Which mechanism is this rho value most consistent with? B, right? It's similar to both in the sense that it's still a positive rho value, meaning the transition state still has buildup of negative charge, but it's certainly not 3, right? And so they use this as evidence that indeed this antibody was catalyzing via mechanism B. And it was an interesting proof of principle because now the idea is, oh, if I can make a transition state analog that looks good enough, looks like a transition state, looks close. Let me try that again. If I can build a transition state analog that sufficiently resembles the transition state for a mechanism I'm interested in, and then if I can evolve an antibody that binds that molecule, all of a sudden I've got an antibody that's a catalyst. And so this is related to the whole field of directed evolution, and instead of designing an enzyme to do something, can you just feed it, can you just give it the right training molecule, and can you, through directed evolution, evolve something that will then have activity? So that's interesting. Catalytic antibodies are still a thing, and you can read about them, but I think we'll stop there. There's some other interesting examples in the book, but I think we've spent enough time on that we'll move on. I guess lastly, I want to say that there are other sigma parameters that people try to use in different situations. Recall that for the benzoic acid deprotonation reaction, we mentioned that if you have electron withdrawing groups here, they can put a positive charge in the ring, but they can't totally delocalize that negative charge. It's a combination of resonance to put the positive charge in the ring, and then an inductive effect to sort of allow this electron deficient ring to pull electron density away from the from the carboxylate group through the sigma bonds. So using these sigma para values doesn't tell you how good a group is at resonance donation versus inductive donation, because you've got both things going on there. So people have tried to parse out sort of how might you do this, and they've done this by using different reference reactions. I won't say anything about the sigma meta values. You get those from doing this same analysis but having the substituent in the meta position. People originally thought, well, maybe this will tell you about resonance versus inductive effect, because for the para substituent you can put the positive charge here, but for the meta substituent it would be here or there, and that's different. And so you can look at those numbers. It turns out that they actually pretty closely resemble the sigma para numbers in some cases. You can explain some of the differences. Look at me. I told you I wasn't going to talk about them, then I started talking about them. For having the meta hydroxy group, this is now no longer a donating group but a withdrawing group, and that's just because perhaps it's now closer to the carboxylate and the electronegativity of oxygen matters more at that point. But if you wanted to see mostly about resonance electron withdrawal, you can use, instead of benzoic acid deprotonation, you can use phenol deprotonation. So vary the X group, measure these equilibrium constants, and then you get a value, a parameter that's called sigma minus, which tells you how good a group is at delocalizing a negative charge. Okay, so sigma minus values are here. And you see, for example, contrasting this acetylated or acyl amine group, acetamide group rather, in the benzoic acid case, it was neither really a good donor nor an acceptor, presumably because nitrogen is a decent donor, but then you put the carbonyl here and that makes the lone pairs hard to donate, and then you've got nitrogen's electronegativity. But it turns out if you do this analysis, you see actually it's not even a donor, it's quite a good withdrawer. Okay? Similarly, you can see that when you look exclusively at resonance instead of an inductive effect, the ketone is really good, is a really good resonance electron withdrawing group. And nitro is an even better electron withdrawing group, right? Here you're seeing a mix and match of resonance and inductive effects. Here you're seeing presumably only the resonance effect. So people will, when they think that resonance is most important in a particular study, they'll use these sigma minus values. You can get sigma plus values for resonance electron donation with using this solvolysis reaction as the reference. Here, you're doing the Sn1 reaction, leaving groups leaving, positive charges on this benzyl carbon that's adjacent to the ring, such that electron donating substituents at this para position could directly stabilize that positive charge. And so here there's a little bit of a switch in order to keep the sign convention similar. You'd expect here electron donating groups to make the reaction faster. And so you'd sort of expect these numbers to be positive, but we switch them so that it's the same, so that the sigma values track with the benzoic acid reaction, so that sigma values that are negative mean that there's an electron donating group. And so those are listed here. And you can see once we get the focus exclusively on the resonance effect, the aniline amino group is a crazy good donor, much, much better than the benzoic acid reaction suggested. And also the hydroxy group is a much better donor than you would have guessed in the benzoic acid reaction. Okay, so just be aware of this, and you may see in the literature people using sigma plus or sigma minus or sigma meta or some combination of them, and understand when they do that they're just trying to account for inductive effect versus resonance. All right, so that's enough, I think, on chapter 8. Yay. We're now going to shift gears and talk about catalysis. So some of our stuff in the beginning is going to be thinking about how catalysts work in general. And then we're going to look at some specific examples of catalysis. We'll talk about Lewis acid catalysis. We'll talk about briefly about organocatalysis. And then we'll deal with acid and base catalysis. And there's this thing called specific acid versus general acid catalysis, or specific base versus general base catalysis. And I've never been able to keep them straight, but I think we'll be able to do it this time. The problem is that general acid catalysis involves using a specific acid that you add. I didn't make this stuff up. Whereas specific acid catalysis involves using hydronium, or the protonated version of the solvent. I know. Why would you do that, right? Like, shouldn't it be opposite? But we'll deal with that later. And some of what we talk about is going to allow us to sort of ask the question: is this protonation step first, or is it after? Okay. And then we'll talk, I think, about Michaelis-Menten enzyme kinetics briefly. So, catalysis. And as they say in the South, bless my heart, I don't understand catalysis like Dr. Michaelis does. So, with that caveat, he can feel free to countermand and contradict anything that I might say. Chapter 9, Catalysis. Okay, principle 1 of catalysis, or how catalysts work, is the catalyst. One way to design a catalyst is for the catalyst to bind or interact with the transition state better than the starting material or the product. By the way, in catalysis, people, rather than say starting material, often say substrate. Is that right? Rachel, do you guys talk substrate? Yeah. Okay. And that's probably by analogy to like enzyme biochemistry, where you have an enzyme and a substrate. Okay. So what do we mean by bind? Well, I think we can generalize that. It could be an actual binding, but we could generalize that to some interaction. It could involve changing the solvation of a molecule. It could involve coordination with a metal. It could involve molecular recognition. It could involve bringing the transition state close, or bringing two reactive groups close to each other. So we're going to be very general in terms of the interaction, but the catalyst has to do something to the transition state that it does not also do to the starting material or the product. And to illustrate why this is the case, let me give you sort of a general example. Let's imagine substrate A interacting with the catalyst through some rate constant, or actually equilibrium constant 1, to give you the complex between catalyst and the A group, or catalyst and substrate A, all right? And then there's a second equilibrium that governs the transition, or rather the second equilibrium that describes the, what the heck am I doing here? K2, equilibrium constant 2, describes the conversion of substrate A into product B, but the catalyst is still bound to and interacting with product B. And then there's some dissociation, equilibrium constant K3, that separates the catalyst and product B, and then the catalyst can go back and do the reaction again and again. All right, so you got a couple of steps. First, catalyst binds substrate to give a substrate catalyst complex. Reaction occurs to give you product catalyst complex, and then product dissociates from catalyst. Does that make sense? And this is true for enzymes, but it's also true for smaller catalysts. So let me give you a picture of what this might look like in terms of an energy diagram. I'm kind of scared. Oops, better draw. All right, so on the y-axis, we're going to have energy. And on the x-axis, we're going to have, yay, generic reaction coordinate. And here we're going to have the energy level of A. About here, we're going to have the energy level of the catalyst complex with A. Then here we'll have, about here we'll have the energy of catalyst complex with B, and then here we'll have the energy of B by itself. All right, so there's some equilibrium between, for A to bind the catalyst, okay? Then there's some transition state, and then B binds the catalyst, and then B dissociates. Okay. Now, we need to compare the catalyzed reaction to the uncatalyzed reaction. In other words, if I were going to convert from A to B without the catalyst, what would that look like? And here I probably am going to wish I had more space. And it's always awkward to like try to span a page when we go to make this a PDF, so I'm just going to move that here, sorry. All right, so let's shrink that down, and in blue I'm going to draw the uncatalyzed energy diagram. So here's the uncatalyzed transition state. Okay. This free energy difference here between A, the energy level of A, and then A bound to the catalyst, this is how much the catalyst stabilizes A, how much binding the catalyst stabilizes A. In contrast, this is how much the catalyst stabilizes the transition state, and then this energy difference tells you how much more stable product B, free product B, is than the complex of B with the catalyst. All right. Notice, and this is an energy diagram that shows you some real catalysis. The reason it works is because the transition state is stabilized by more. The catalyst stabilizes the transition state by more than it stabilizes the starting material. What does that do for us? Well, what's the activation energy for the uncatalyzed reaction? That's the energy to go from here all the way there. Okay? In contrast, the activation energy for the catalyzed reaction is just to go up that high. Now, what would be the problem if the transition state, what would be the problem if the catalyst bound the starting material more tightly than it binds the transition state? Should we try to draw that? I'm going to copy this energy diagram just to illustrate this issue. Let's suppose that, actually, I wanted the transition state just like that. Sorry, I wanted that there. We'll erase this. And let's keep everything else the same. So notice that here our catalyst lowers the free energy of the starting material by maybe a square and a half. Okay, so let's do the same here for our transition state, maybe a square and a half. This is now the catalyzed transition state. Have we done ourselves any favors? Is the reaction going to be faster? No. We have defeated the purpose of catalysis, because if we stabilize the transition state by the same amount as we stabilize the starting material, we got nothing going on here, right? You can't accelerate the reaction. You can't make the activation energy lower if you're going to do this to the transition state and the starting material in parallel. Just doesn't work. So this would be a not catalytic catalyst. Okay. What would be the problem? We don't need to draw another energy diagram for this. What would be the problem if the catalyst bound the product more tightly and stabilized the product such that the product bound to the catalyst was more stable than the product that's free? What's the problem there? If this energy of the catalyst product complex is like down here. Go ahead, Rachel. You don't get any of the product. Why?
Because the transition state is too high.
Yeah, because the catalyst stays bound. The product doesn't ever come off the catalyst. So you have to remember, when designing a catalyst, you got to imagine that at some point the catalyst has to let go of, it's like letting go of children and letting them go away. You try to raise them right. This is on my mind because of my 18-year-old son who never texts us except when he wants something. He texted us last night. He's like, Dad, we're in a Christmas decoration war with other apartments. Do you have any more Christmas decorations you can give me? So, but yes, you want the little bird to leave the nest eventually, right? And that can't happen if the catalyst makes the product too stable. All right. Now, finally, you can imagine a crazy bad catalyst that would bind the starting material more tightly than it binds the transition state. And in that case, that would be like, what if you bound the starting material but you did nothing to the transition state? Now you just made your life worse. So that's not a catalyst, that's an inhibitor. Okay? And maybe you want to do that, right? Maybe you want to stop a process from happening. But most people that claim to be working on inventing catalysts, that's not their that's not their purpose. Okay. So the moral of the story is, when you're thinking about catalysis, it has to do something to the transition state that it's not doing to the starting material. All right, any questions about that? Okay. Principle 2, Rachel, I think you'll be familiar with this. You can probably guess it. You don't work on the peptide project, do you? No, but you know people who do, right? So Michaelis's lab has a peptide where they bring one group here on an alpha helix and another group here, and they're hoping that this can catalyze a reaction. How does this work? Do you know? Like, what's the idea that would make this reaction work?
I think it's because it's like something about proximity. Like, it's like they tested at like the I position, I+2, I+4.
Okay.
And so I think it has something to do with proximity.
Right. So imagine you have molecule 1 and molecule 2 that react together to make a product. And in the uncatalyzed reaction, they have to find each other. But the idea in the Michaelis lab is, can we bind catalyst, can we use some group to bind molecule 1 and another group to bind molecule 2 and at the same time activate molecule 2. Now they're close together. Now it's an intramolecular process, and we just learned about that in chapter 8. Effective molarity goes way up and you can accelerate the reaction that way. So principle 2 is proximity. Take advantage of proximity effect. The rate of the reaction between molecule 1 and molecule 2 is going to be related to how often molecules 1 and 2, how frequently they spend time together, how close they are together. All right, so I think that's a good place to stop for today.